So next speaker is Matthias Gaberdiel, and he will tell us about the string dual of free n equals 4 supermills.
Okay, well, thank you very much for the introduction and invitation. I would have loved to come to Heidelberg, but unfortunately I couldn't get away from Zurich, so it has to be remote. Okay, so my talk is somewhat has a different style than many of the other talks. So I'll try to motivate it in a way that maybe also people from a little bit further afield can understand what we are up to. So this is about the Adscft duality, and I think what you need to know about it is that this is an important problem in string theory to understand really how it arises. It is very influential because it relates to rather different theories to one another, namely some superstring theory on an ADS background to a gauge theory living on the boundary, and this has been extremely influential over the last 25 years or so. Now, there is very much evidence that this duality is correct, that it captures interesting dynamics, that it's not just kinematical, that there are plenty of consistency checks that have been performed. But I think we are still short of a real proof. And I also think this is more than some sort of aesthetic or nice to have situation. We would like to apply this duality in situations that are not directly ADS 5 versus 5, say. And in order to do so, we have to have a better understanding of what really makes this duality work, how general it is, what pieces are crucial, what pieces are accidental, and so on. And I think unless we understand the duality, at least in one example, in great detail, we will not be able to understand what exactly makes it tick. So what our aim has been for the last essentially 10 years, and so this is largely based on work with Rajesh Goprakuma, involving also some other people, as I mentioned as I go along. So our aim is to try to derive the Adscft duality in at least one simple setting, to understand how it works there, and then maybe understand more general lessons from it. So sometimes we hear people say that the Adscft correspondence is a strong weak duality. And this comes from the fact about how the parameters of the string theory side of the picture and the gauge theory side are related to one another. And very roughly, I mean, but this is sort of the essential piece that you have to take away from it. There are really two independent parameters that characterize the two theories, and they're related in a very specific manner in the context of this Adscft correspondence. So there's the rank of the gauge group, which is n, and the rank is inversely proportional to the string coupling constant. And we should always look at the situation where n is large, so that the string coupling constant is small. The string coupling constant is the measure. It's the coupling constant that tells you the probability for a string to split, for higher genus contributions relative to the lowest order contributions from a string worldsheet perspective. So that side is fine. I mean, we want to be at large n. The gauge theory simplifies at large n, and we want to be at small g string. So that's a no-brainer what we should do there. The other, I mean, it's really a two-parameter space. We got really two parameters. One is the string coupling constant, and one is the radius of the ADS space, or the inverse cosmological constant, in terms of the typical size of a string, what is normally called the string length, or LS here. Now, this quantity, according to this dictionary, is proportional to what's called the Tuft parameter. The Tuft parameter is a certain combination of the coupling constant and the rank of super-Yang-Mills, and it is the effective coupling constant of the gauge theory in the large n limit. So if I take n large, then the Tuft parameter characterizes the effective coupling constant of the gauge theory. And what this dictionary tells you is that this coupling constant is to be identified with some power of the radius in terms of string units. So this is where people normally, this is the reason why people normally say Adscft is a strong weak duality, because you see, if you take the Tuft parameter small, then that means the radius is of the same order of the string length, i.e. the system is extremely stringy, and that's a regime that's not that easy to access. from the ADS side. From the ADS side, it's easy to access the regime where the radius is much bigger than the string length. That's the regime in which you can describe it in terms of supergravity. So that's the regime where this is sort of perturbative, but then this corresponds to the coupling constant in the gauge theory to be large. So one side is always under good control and the other side is under poor control. And that's what people usually refer to when they say it's a strong weak duality. Inherently, it's very difficult to prove because typically you have one side under control and not the other, but not both sides at the same time. So this is the basic problem why people haven't proven the ADS-CFT duality many years ago. It's not so obvious how you're going to do it. Now, if you think about it, on the gauge theory side, we have very little choice. I mean, on the gauge theory side, we are very far away from understanding strongly coupled gauge theory. So we are de facto forced to choose lambda to be small. So when you do that, what this means is that the radius in terms of string units is small. And another way of saying this is that the size of the string is relatively large, or rather the string has the same size as the space in which it propagates. So this is usually referred to as tensionless strings. And this is the regime of string theory that corresponds to the situation where the Tuft parameter is small, i.e. to the weakly coupled gauge theory regime. And this is an old idea. This was observed many years ago, that this is a regime where also something miraculous should happen on the string theory side, but you are very far away from the regime that people usually study, i.e. you can't describe the background in terms of supergravity. Now, what would you expect to happen on the string side when you look at this weakly coupled Superang-Mills theory? You should expect, you see, weakly coupled Superang-Mills theory is a free theory, well, essentially free theory. So it has lots of symmetries, and somehow they should be reflected on the string theory side. And the idea is that while you can't describe it in terms of supergravity, there should be some other redeeming feature that allow you to make sense of string theory in such a background. And the basic idea or the basic tenet behind what we have been trying to do is that because this is so symmetric, it has this higher spin symmetry and so on, you may hope that while the supergravity description will be extraordinarily complicated, maybe it will have a simple worldsheet description. So as you probably know, the fundamentally correct way of describing string theory is in terms of the worldsheet of the string maps from the worldsheet into the target space. And what you could hope is that the weakly coupled Superang-Mills regime corresponds to a string theory that is very complicated because it's highly curved, but maybe it has a simple, a solvable, maybe even a free worldsheet description. So this is sort of our working hypothesis. This is our idea that that's maybe is the regime where we have a chance to prove ADS-CFT. And what we should be looking for is what can we say about the honest string description in this tensionless regime, and can we make sense of this worldsheet description concretely? Now, this is sort of, I mean, it's very general so far. So you can ask yourself, I mean, is there any evidence that this seems to work? And in fact, there is we feel there is relatively good evidence for this to work, at least in the case for ADS3. So ADS3 is the three-dimensional anti-de Sitter space, and the background string theorists like to look at is the three-dimensional anti-de Sitter space times a three-sphere times a four torus. That makes up the 10 dimensions of critical superstring theory. And originally part of the original Maldacena proposal was that this should be dual to a certain two-dimensional conformal field theory, namely to the symmetric orbifold of T4, which is nothing else that you take n copies of T4, and then you divide by the symmetric group, which permutes the n copies. So this is some sort of on the same level as ADS5 × S5 and n = 4 Superang-Mills. This is sort of a part of the string folklore that these two descriptions are dual to one another. Now, obviously, one has to be a little bit careful because there's a whole moduli space of these conformal field theories. And the symmetric orbifold theory is one specific point in this moduli space. But what one may believe is that this symmetric orbifold point is really the analog of free Superang-Mills. I mean, you see, it's the four torus, which is basically four bosons, four free bosons and four free fermions. You take n of them, so you have 4n free bosons and 4n free fermions. And then you just divide by some global group, which is like the sort of gauge invariance of Superang Mills. So you could believe that the symmetric orbifold theory is really the lower dimensional analog of free Superang Mills. So you would believe that this is the analog of the Tuft parameter being small. So you could ask, can we identify the dual worldsheet theory? And can we see that there is something very special happening for this worldsheet theory? Now, what we propose and what by now we have very good evidence for, and I'll review some of this evidence, is that in this limit, that the corresponding string theory is the background ADS3 crosses 3 at the tensionless point where it is very, very small. And I'll explain in more detail what I mean by this level here. But in fact, in terms of this so-called hybrid formalism of Berkowitz, Waff, Witter, it means that you have to take the super Lie algebra PSU 1,1/2 at level 1. And the super Lie algebra arises because that describes the geometry, the symmetries of ADS3 crosses 3. So in any way, what we propose is that a symmetric orbifold theory is exactly dual to a very specific string worldsheet theory. The string worldsheet theory consists of 4 symplectic bosons and 4 free fermions, which furnish a free field realization of the super Lie algebra, super affine Lie algebra PSU 1,1/2 at level 1. And what we've shown, and I'll review this a little bit later, is that if you apply the usual string procedure to this worldsheet theory, you reproduce exactly the degrees of freedom of the dual symmetric orbifold, and you also recover the structure of the correlation functions. So this is an example where we've gone very, very far towards actually proving the ADS-CFT correspondence. We've written down a specific worldsheet theory. We can analyze it because it's a solvable worldsheet theory. We can determine the physical spectrum, and it matches exactly, not just on the BPS level, the entire spectrum reproduces exactly the single particle spectrum of the symmetric orbifold of T4. And furthermore, the structure of the correlation functions are also correctly reproduced. Now, this is what the first half of my talk will be about, to try to review for you how this comes about and the sort of structure that we see. Now, what we've been thinking about during the last few months, in particular this year, is whether we can sort of boost this up to actually find the worldsheet description for free n equals to 4 Superang Mills in 4 dimensions, i.e. going back to the sort of higher dimensional case. And again, that should be a tensionless string theory. And what we propose is that you basically just double the degrees of freedom from the ADS3 theory. So instead of having 4 symplectic bosons and 4 free fermions, we propose that the worldsheet theory consists of 8 symplectic bosons and 8 free fermions. And this, as it's not difficult to see, furnishes a free field realization of the Lie algebra PSU 2,2/4 at level 1. And as a consequence, at least the global symmetries of n equals to 4 Superang Mills come out correctly. It's also similar to other ideas, in particular this twistor string of Berkowitz. And I'll try to motivate our proposal and then explain to you to which extent we've managed to see that this really reproduces at least the correct spectrum of free n equals to 4 Superang Mills. So there are still many gaps in our argument. This is at a much earlier stage in the development, but we feel this looks very promising, and it has all the right ingredients to describe the worldsheet description that's exactly dual to free n equals to 4 Superang Mills in 4 dimensions. And therefore, it really opens the door towards having a serious go at proving the ADS-CFT correspondence in that context, because both theories are under quantitative and detailed control. So we should be able to really check this in great detail and derive the duality, and hopefully that will teach us more general lessons about ADS-CFT. So this is sort of what I want to explain to you. So what I want to spend about half of the talk is or probably even a little bit more than half of the talk, to review how ADS3 works. Then I want to explain to you why this motivates this generalization to ADS5 and what we can say about ADS5. And then I'll end with some conclusions and outlook for where we hope to go in the future. If you have any questions, please feel free to interrupt. So let me start by trying to explain to you in a little bit more detail how this ADS3 story really works. So the ADS3, the string theory in ADS3 crosses 3 you can describe in terms of what's called the Maldacena-Oghori-Wessel-Minowitsch model, and that is a fine description of it. But there's an alternative description that was invented by Berkowitz, Waffer, and Witten, primarily with the aim of switching also on Ramond-Ramond flux. But if you don't do this, if you just look at the pure Neveu-Schwarz backgrounds, then their description is basically like the Green-Schwarz version of the NSR version a la Maldacena-Oghori. And the key feature of it is a super Wessel-Minowitsch model based on PSU 1,1/2. That describes ADS3 cross S3. And then you have a topologically twisted sigma model on T4, i.e. you just have 4 free bosons and 4 topologically twisted fermions. And then you have a cohomology that describes for you what the physical states of this worldsheet theory should be. And I mean, they derived it by starting with Maldacena-Oghori and doing some sort of field redefinitions, but you can also check that the spectrum agrees, and that has, I think people believe that this is exactly the same description. Now, what we are interested in is this theory at level 1, because you see the level of this is basically the size of the ADS3 cross S3 space. So K being large would correspond to ADS3 being and S3 being big in string units, and K small means ADS3 and S3 are small in string units. And remember, we are trying to find the analog of the tensionless string. So this should mean the regime where this is very small. So you want this, take this at the smallest possible value that makes any sense. And the smallest possible value is K equals to 1. So we want to study the PSU 1,1/2 Wessel-Minowitsch model at level 1. Now, as people know, level 1 theories, say for SU2 or SUM, they're very special, right? They're quite different from the Wessel-Minowitsch model corresponding to SU2 at level K. They contain far fewer degrees of freedom. And as is famously known, SU2 at level 1 is really equivalent to a single circle. So the structure of it changes dramatically. So one may hope that also for this super Lie algebra, something special may happen at level 1. Now, the first indication that something special may happen is if you look at the Bosonic Sub-Algebra of this super affine algebra. So the Bosonic Sub-Algebra is just SL2. So SL2 is basically the same as SU1,1. So whether you call it, so this is really the Bosonic algebra is SU1,1 and SU2, but SU1,1 I call SL2R, but this is really meant to be the same thing. And then the SU2 factor is the SU2 factor. And the way this Bosonic sub-algebra sit inside this super affine algebra is that the levels are the same. So in particular, you end up with SU2 at level 1. But as I just mentioned to you, SU2 at level 1 is quite a special theory. In particular, it only has 2 highest rate representations. I mean, as people probably know, SU2 at level K, the spin of the highest rate space can go up to K over 2. So the spin can be 0 or half for the case at level 1. And if you translate this into a dimension, it can either be the singlet or it can be the doublet with respect to SU2. So that's purely if you look at the SU2 part. But think about it, PSU 1,1/2 is a super Lie algebra. It has fermionic generators. And therefore, the highest rate states of a highest rate representation will sit in some sort of Clifford algebra coming from the fermionic zero modes. And you can organize the different terms in this Clifford algebra in terms of representations of SL2R and representations of SU2, which is what I've done here. So here, the first entry always describes the representation of SL2R. And I'm looking at the so-called continuous representation. So the spin is parameterized as a half plus IS. And alpha, this parameter alpha, labels for you the eigenvalue of the Cartan generator of SL2R mod integer. These are the 2 parameters that characterize the SL2 representations. And the second entry here is just the dimension of the SU2 representation. Now, this is the generic representation of these fermionic zero modes. And if you stare at them, then you observe that, you see, if you start here with n, there is a term here that will involve n plus 2. But on the other hand, remember, for SU2 at level 1, the only allowed representations are n equals to 1 and n equals to 2. So even if I start with n equals to 1 here, I would get a representation that's not allowed here. So therefore, at level 1, the only representations that are compatible with the structure of this vertex operator algebra are the short representations. They must be shorter than the generic representations because the SU2 representations can't support highest rate representations where the spin is bigger than a half. So you can analyze this, and what you find is that apart from obviously the vacuum representation, the only allowed representations are these extremely short representations that consist of 3 summands. So this is basically a piece of that, but you basically just keep these 3, and all the other ones are set to 0. They must be 0, otherwise it's not a representation. So you have a strong shortening condition. And then if you study it, you find that this shortening is only possible if the spin that enters here in terms of these SL2R representations is actually equal to a half. You can't take any other value of the spin. So this representation theory, which to start with looks very, very floppy, seems to contain all sorts of stuff. At level 1, there's really essentially only one representation. Well, you have one free parameter, which is this alpha parameter, but apart from this alpha parameter, everything is fixed, and that's the only non-trivial highest rate representation apart from the vacuum representation. In particular, there's no continuum, and for people who sort of know the background of this a little bit, the continuum of this Wessel-Witten model was always deemed to be the reason why it can't be due to the symmetric orbifold, but at level 1, the representation theory is much more rigid. The continuum isn't there, and there is a chance that it matches with the symmetric orbifold, and as I'm about to explain to you, it in fact matches exactly with the symmetric orbifold. Okay, so this is the representation theory of PSU 1,1/2 at level 1. There are other ways of deriving it. In fact, there's a very useful way to think about PSU 1,1/2 at level 1, which is the fact that it has a free field realization. I mean, this is the way you should think about it, is that this is really the super algebra version of SU2. So SU2 at level 1 has a free field realization, say, in terms of a complex fermion modulo U1 or a single real boson. And likewise, the PSU 1,1/2 has a free field realization in terms of free fermions and what you may want to call symplectic bosons. So to be a bit more specific, the algebra that has a free field realization is U 1,1/2 at level 1. And it can be written in terms of these fields. So these are the standard fermions. They just satisfy usual anti-commutation relations. And then you have what are called symplectic bosons. So they look the structure of the right-hand side looks like 4 fermions. So they seem to be spin a half, but they satisfy commutation relations rather than anti-commutation relations. So that's what that's what often called a symplectic boson. So they behave like a ghost. But these are the fields that generate, if you look at the suitable bilinears of them, they'll generate for you U 1,1/2 at level 1. And then in order to get PSU, you have to sort of gauge by some diagonal U1, and the diagonal U1 has basically this form. You basically couple the 2 symplectic bosons together and the 2 fermions together, and you sum over everything. And that's the thing you have to set to 0 in order to go from U 1,1/2 to PSU 1,1/2. So that's another way of describing this worldsheet theory. So in particular, we should be able to recover the structure of the representations from this free field description. And that is as straightforward as it goes. You see, these fields have basically a Ramond sector and a Navier-Schwarz sector. You have to choose all of them to be either in the Ramond sector or in the Navier-Schwarz sector. All of them should be half integer moded, or all of them should be integer moded. Because you see, the bilinears always have to be integer moded. So you have to choose the mode number once and for all. If you take them all to be half integer moded, then you just describe the vacuum representation of PSU 1,1/2 at level 1. And if you describe them all to be integer moded, you describe this short representation that I talked about before. So these are the only highest rate representations that this super Lie algebra has. So they will therefore appear in our spectrum of our worldsheet theory. So here's a sketch of what this looks like. You see, the symplectic bosons, they don't satisfy an anti-commutation relation. They satisfy a commutation relation. So you can go infinitely many times in either way, in this way. So unlike the fermions, this will not be a finite dimensional representation. It'll be an infinite dimensional representation. You can apply psi plus as many times as you like, and eta minus and so on. And you just walk to the right or to the left as many steps as you want. And then you have some choice exactly of how the offset is. And this choice of the offset translates into this alpha parameter that I was referring to earlier. So this is basically just reproducing this representation theory that I described for you before, more concretely from this free field perspective. Okay, so these are the highest rate representations, but And this goes back already to the papers of Maldacena-Oguri. String theory in ADS3, process 3, doesn't just consist of these highest rate representations. What you have to do is you have to, in addition to these standard highest rate representations, you have to add in what are called spectrally flowed representations. So these are representations that you obtain from these highest rate representations by applying a certain outer automorphism of the PSU 1,1/2 algebra. So what's the outer automorphism? Well, it's most easily described in terms of the free fields. So I can define tilde modes and untilde modes that are related to one another in this fashion. And they clearly describe an automorphism because you see the commutators, they only care about that the sum of them has to be equal to 0. So as long as I shift one up and the other one down, the commutators will go into the commutator. So these are is an automorphism of this free field algebra. And then if you translate this into the generators of the PSU 1,1/2, you see that the Cartan generator transforms as such, and the Virasoro generator transforms as such. And I'm here only spectrally flowing the bosons. You can also spectrally flow the fermions, but whether you do or not is really a matter of choice. Now, when you do this, you see what happens is that the L0 eigen, so what you do is you take the standard Ramon sector representations, you regard it as a representation of the tilde modes. So the tilde modes act on this space like it's written, but then you interpret it as evaluated with respect to the untilde modes. So in particular, you can ask yourself, what's the L0 eigenvalue on this space? The L0 eigenvalue is what the L0 eigenvalue used to be minus W times what the J30 eigenvalue used to be. But because this representation is infinite in both directions, you see the J30 eigenvalue can go as positive as it wants for a given L0 tilde eigenvalue. If you go further to the right here, then L0 will get more and more negative. So these spectrally flowed representations are not conventional highest rate representations. They're really inequivalent representations relative to the familiar category of highest rate representations of the super affine Kac-Moody algebra and the super affine algebra. And the observation of Maldacena-Oguri, and that's also reasonably well motivated from string theory, is that you need these representations on your worldsheet description in order to describe string theory on ADS3 crosses 3. I mean, the reason is basically, you see, when you describe string theory in Minkowski space, the L0 spectrum on the worldsheet is also unbounded because you need to have sufficiently, I mean, you want to have arbitrarily many excitations, but still satisfy the Maxwell condition. So your L0 spectrum, before you impose the physical state condition, must be unbounded. And the same is true here. This is basically why you need these spectrally flowed representations so that you get an unbounded L0 spectrum so that the resulting physical spectrum has a chance to look like anything like a string. Anyway, that's the old proposal of Maldacena-Oguri, that you take the representations, the highest rate representations, and you add in the spectrally flowed images, and that describes your full worldsheet theory. And we are simply doing exactly the same thing here. In our case, we are taking, in fact, just a Ramon sector representation. The Neveu-Schwarz sector is sort of measure 0 and doesn't appear. And we add in all the spectrally flowed images, and that describes our worldsheet theory. That describes the Hilbert space of the, well, not Hilbert space, it's a non-unitary theory, so that describes the vector space of your worldsheet theory describing string propagation on ADS3 crosses 3. Now, since this PSU 1,1/2 theory has this free field realization, or because it has many null vectors, whichever way you want to look at it, it has far fewer descendants than you would naively expect. In particular, you see from the point of view of the free fields, you have 4 symplectic bosons to start with, but you have to divide out by this U1 constraint, and that effectively eats you 2 bosons. So you have only 2 bosonic degrees of freedom left after you've gone to PSU starting from U 1,1/2. On the other hand, as many of you are familiar with, whenever you look at the string spectrum, you basically have to impose the physical state condition, and the physical state condition typically eats 2 transverse degrees of freedom. So this naive counting suggests that after you've imposed the physical state condition, there are no transverse degrees of freedom left from the ADS3 crosses 3 factor. And therefore, you would expect that all the degrees of freedom will come from the remaining T4 factor. Because remember, it's ADS3 crosses 3 cross T4. The PSU bit only describes ADS3 crosses 3. So what this argument tells you is that in the physical string, there won't be any excitations on ADS3 plus S3. All the excitations will come from the T4. And if you go through the systematics of it, what you find is that you reproduce exactly the single particle spectrum of the symmetric orbifold of T4. So you take this worldsheet theory, you apply the standard rules of string theory, you look at the physical states, you can enumerate them because it's a free field theory. And what you find is that it matches exactly the single particle states of the symmetric orbifold of T4, i.e. it reproduces exactly what we thought should be the dual CFT. And the way the dictionary works is that the W cycle twisted sector of the symmetric orbifold, I'm not going to go into detail what that is, but that's a specific piece of the symmetric orbifold theory that comes exactly from the sector with W units of spectral flow, i.e. from the sector where you have done this for W being the corresponding number, the corresponding integer. So this is quite striking already because that gives you, reproduces exactly the spectrum of this dual CFT from the worldsheet, and not just for the states that are protected by supersymmetry, it reproduces the entire set of physical degrees of freedom. Now, furthermore, you can ask yourself, how about the correlation functions? I mean, whenever you want to show that two things are the same, two theories are the same, you typically want to show that the spectrum agrees, and then you want to show that the correlation functions agree. So what can we say about the correlation functions? Now, the correlation functions of the symmetric orbifold theory have quite a remarkable structure. So suppose you're looking at a symmetric orbifold theory and you're evaluating it on a sphere, that is the boundary of ADS3 is a cylinder. So if you compactify it, you get a sphere. So you're going to calculate these correlation functions on the sphere. There's a smart way of calculating these correlation functions by going to the so-called covering map, by looking at some surface that covers the space where your symmetric orbifold vertex operators are inserted, and you're looking for a holomorphic map from some Riemann surface down to the sphere so that near each of the insertion points up there, you get mapped to a point down here. So xi gets mapped to zi gets mapped to xi, but near z equal to zi, there's a critical point in the sense that it maps it to zi gets mapped to xi, but in the neighborhood, you cover it wi times. So this is a statement about how symmetric orbifold correlators can be calculated, and that goes back a long time. On the other hand, it's quite natural, if you look at the 1 over n behavior of these correlators, it's quite natural to believe that this covering surface should be identified with the worldsheet of the putative string theory, because then the way the genus appears in this correlation function calculation for the symmetric orbifold captures exactly how the genus expansion of string theory should appear, given that the G-string coupling constant is related as 1 over n, as I mentioned earlier. So what it suggests is that maybe the worldsheet theory should play the role of the covering surface, but that should mean that if you calculate the worldsheet correlation functions in this funny theory, what you may hope for is that they localize exactly to those configurations where such a holomorphic covering map exists. So the statement that was proposed some time ago by Pachmann, Rastelli, and Razamat, and that we've now managed to establish from first principles, is that if you look at this PSU1,1/2 theory, you calculate the correlators of this vertex operator corresponding to spectrally flowed sectors, then these correlation functions are mostly zero. I mean, they're generically zero, and they're only non-zero provided that the ZIs, which are the points where you insert them on the worldsheet, conspire in such a way that you have a holomorphic map from the worldsheet to the space in which the dual CFT lives, such that Zi gets mapped to xi, and near Zi, the function has this form. This is a highly constraining property, and in fact, the set of covering maps is discrete. That's described by Hurwitz's theory. So there's a nice story about how this comes. But quite remarkably, what we find is that these correlators calculated in this PSU1,1/2 Wessel-Minowitsch model at level 1 have this very remarkable property that they are essentially always zero except when a covering map exists. And they take exactly this form. And you see, once they take this form, then when you do the integral over the worldsheet moduli, as you have to do in string theory, you have to integrate over the insertion points on the string moduli, as well as the parameter that describe for you the shape of the torus and so on. if you do this integral, then there are exactly enough delta functions to turn this integral into a finite sum over the covering maps, and you reproduce essentially manifestly the answer that you can calculate directly from the symmetric orbifold. So this picture really quite suggestively reproduces all the structures that you know from the symmetric orbifold from what is essentially a free worldsheet theory, and a worldsheet theory that you can really construct and calculate, and for which you can establish statements like that, where you can really calculate these correlation functions and show that they have this property. In fact, the most elegant way of showing this property is not directly in terms of PSU 1,1/2, but again in terms of these free fields. And what we found is that these correlators satisfy this remarkable property that this combination of the symplectic bosons vanishes inside any physical correlator, where here you write down the covering map that maps the z's to the x's. So, and what you can show is that the covering map exists. That what it basically tells you is that the covering map is minus psi minus over psi plus. So you can express the covering map in terms of the symplectic bosons. And if the covering map doesn't exist, then the individual correlators have to be 0. And you can furthermore show there's really a delta function localization. So this is the status of ADS3. And in that case, we've really matched the spectrum and the correlation functions essentially from first principles. And we have a very good and detailed understanding of how this duality works. Now this relation, if you know a little bit of twistor theory, this relation looks a little bit like the incidence relation in twistor space. I mean, this is to be identified with the coordinates of the space-time theory. So this really looks like two twistor fields being related by the coordinates. That looks like the way you go from the twistor space to the physical space. So this suggests that maybe the right way to think about this theory is that these free fields are really living in the twistor space of our space-time theory rather than just being randomly chosen free fields. Now, if you believe that, that sort of suggests rather naturally what the generalization to ADS5 cross S5 could be. Because you see, for ADS5 cross S5, you would expect you would need the twistor space description of the four-dimensional boundary, or the ambitwistor description of ADS5 cross S5. Of ADS5. And when you look at that, and this goes de facto back already to older work of Berkowitz, I mean, he proposed that the twistor theory should be written in something which he didn't call symplectic bosons and free fermions, but if you look at what he's done, that's really what they are. And in his description, there were additional fields and he didn't have spectral flow, so the theory was somewhat different, but the ingredients were rather similar. And what's striking is that these free fields, they generate U2,2/4. And then if you remove again a U1, just like as before, you get to P as U2,2/4, which is the global conformal symmetry of n equals to 4 superconformal Young-Mills. So you seem to be landing on your feet. Just like, incidentally, P as U1,1/2 is just the n equals to 4 symmetry of the conformal field theory together with the R symmetry of the SU2. So what we propose is that we should consider the worldsheet theory where we have 8 symplectic bosons and 8 fermions. We don't have a T4 anymore. So basically the T4 gets replaced by another set of 4 symplectic bosons and 4 free fermions. So they basically looks exactly like what we had before. So everything is doubled. So we have 2 sets of symplectic bosons and now we have 4 sets of fermions. And as I mentioned before, this looks exactly like what Berkowitz had proposed in 2004. So you have 2 pairs of these, and then you have 4 of these. And this is what we take to be our worldsheet theory. And as it's not difficult to convince yourself, if you look at the bilinears of them, where you combine one of these and one of these, then you produce U2,2/4. And then if you divide out by this U1 field, you produce the P as U2,2/4. And in fact, this is really just the affinization of what's called the oscillator construction of P as U2,2/4 that enters into the spin chain description of n equals to 4 super Young-Mills. So this is again making contact with stuff people have seen in another context of describing n equals to 4 super Young-Mills, namely in terms of this spin chain description that exhibits the integrability structure that's underlying this. Okay, so now I think the new ingredient that we added to this story is that, first of all, we don't add any additional gauge fields like Berkowitz did, but maybe more importantly, we expect this theory also to have spectral flow, just like the ADS3 theory had. Now, in the ADS3 theory, while I didn't say it explicitly, the way which modes get moved upwards and downwards is basically determined by the eigenvalue of J30 minus K30, where J3 and K3 are the Cartan generators of the SL2 factor and the SU2 factor. So the natural analog for ADS5 is that you take the corresponding, the J30 becomes the conformal dimension in target space. So here we take the dilatation operator, which becomes the conformal dimension in n equals to 4 supermills. And K30 is a certain R-symmetry generator, so we replace it by some R-symmetry generator of the SU form. And that leads to the proposal that the spectrally flowed sectors should have that structure, that you should spectrally flow these symplectic bosons and fermions as written here. And then we do exactly the same as we did for ADS3. So we start with some representation. In this case, let's start with the Neveu-Schwarz sector representation. It doesn't really matter, but it's slightly more convenient to describe it that way. And then as before, you see this relation. As I said before, you think of this as being the standard way to act on the Neveu-Schwarz sector vacuum. So these modes kill it if R is a half or bigger. So this means that these modes kill it if the mode number is W plus 1 or bigger. So you find that these modes will kill the ground state if R is greater than W plus 1 over 2. These for the fields that have a plus sign here. And for those that have a minus sign, they behave exactly the opposite. So for them, they annihilate the ground state provided R is greater than minus W minus 1. Okay, so these are the fields that kill, but because it's a free field theory, everybody that doesn't kill creates. It's a Fock space. There's nothing fancy happening here. So if these modes kill, all the other modes don't kill. So what are the modes that don't kill? Well, from the first line, you get everybody where R is greater than W minus 1 over 2. So, sorry, R is less than W minus 1 over 2. And from the second line, you get everybody that where R is less or equal than minus W plus 1 over 2. So I can say that the first line contributes inside this wedge, and then everybody contributes if the mode number is less than minus W plus 1 over 2. So this is simply the Fock space description of the spectrally flowed representation written in terms of these free fields. Now, unlike the situation in the Berkowitz-Vafa-Witten story for P is U1,1/2 or ADS3/3, they had constructed for you a cohomology, and you knew, at least in principle, how you would determine the physical spectrum. Here, we are a little bit on our own. We've just guessed a worldsheet theory, and we have yet to define the cohomology that will characterize the physical states. And we are working on that, but this is likely to be not an entirely trivial problem, but you can guess maybe what the answer will amount to. So our guess is, and this is a postulate at that stage, that the physical state condition will amount to imposing something like an n equals to 4 critical string condition, and that its effect will be that all of the modes that are what we call out of the wedge, where the mode number is sufficiently negative, are unphysical. This is, basically you have twice as many gauge constraints, so this will remove 8 plus 8, 8 fermions plus 8 bosons. So it's plausible that this will remove all of these degrees of freedom, and we propose that all of the modes that are sufficiently negative get removed. So that only leaves you with this finite set of modes, and the finite set of modes you want to think of as being some sort of generalized zero modes. So instead of having a copy from the left and having a copy from the right separately, what we furthermore propose is that you only keep one copy from them, because they're somehow like zero modes that are shared between left movers and right movers. And that's a little bit inspired by this flux vacuum solutions, which were studied for this Berkowitz theory in these two papers in particular. But I should be honest with you. This is a very much a postulate at this stage. We would very much like to derive it from first principles. But I think our attitude is, since this leads to the right answer, there must be a way of finding a cohomology that will reproduce that, and that will be the correct cohomology to describe our string background that will be due to free n equals to 4 supermills. Okay, so we're not entirely done yet. So we throw away all of these out of the wedge modes. We keep the wedge modes, and then we have to impose residual gauge conditions. So one residual gauge condition is pretty obvious. You see this U1 condition we've sort of forgotten along the way. So we still have to impose this U1 condition, So remember, this comes from the U1 you have to divide out by in order to go really to PSU1, PSU2,2/4 rather than U2,2/4. So we still have to impose that. And then you would expect there's going to be some sort of Virasoro condition. And what we postulate is that the correct version of the Virasoro condition takes this form, that L0 doesn't necessarily have to be 0. It just has to be a multiple of W in the W cycle twisted sector, and sorry, in the W spectrally flowed sector, and that you can motivate by analogy with the BMN limit and so on, but I don't want to go into that in any detail. Now, again, this is a postulate. We have no direct way of deriving this from first principles, but in our opinion, this is a very plausible postulate. And once you accept this postulate, then we can just ask what space of states do you produce? And what we can show, and I'll just sketch for you the argument in the following, the resulting spectrum reproduces then exactly that of free n equals to 4 superangles in the planar limb. Now, maybe you say a free theory is not that tricky, but if you actually look at the spectrum of free superangles in the planar limit, even that is not entirely trivial. So this is already a somewhat non-trivial statement that you reproduce that part of the spectrum. So how do you see that this really works out? Well, the smartest way of doing this is so remember, we have these wedge modes. So let's call these wedge modes collectively Zi with R running in this wedge. Then you want to think of them as being the momentum modes whose Fourier transform would give you position modes associated to the corresponding field. And because you have W momentum modes, you're going to have W position modes. So this begins to look like a spin chain with W sides, and at each side you can put one of these Zs. And in fact, if you do this and you just follow the commutation relations, then these position modes sitting at different sides pairwise commute. So this really looks like a localized spin chain where at any spin side you have the degrees of freedom coming from the Zi's and the Yi's. Now then the residual gauge conditions, if you also Fourier transform them, what they imply is that you can either impose this in sort of momentum space, or if you transform them into position space, what this implies is that at each side, you impose the condition that C is equal to 0. So at each side, you have the Y's and the Z's. They generate you a copy of U1,2,2/4, and then you impose the Z condition, the C condition, and that basically imposes that you're really working with PSU 2,2/4. And in fact, if you go through it, what you find is that at each side, you will keep the so-called singleton representation of PSU 2,2/4. That's a certain infinite dimensional representation of PSU 2,2/4. And then the Virasoro condition, if you look at it, what it implies is that you get that these, so you have W sides, at each of them, you have a copy of the singleton representation. And then the Virasoro constraint simply forces that this W-fold tensor product of the singleton representation, has to be invariant under the cyclic transformation. So what this means is you keep the cyclicity invariant piece of the W-fold tensor product of the singleton representation of PSU 2,2/4. And that is a fact that has been known before. That is exactly the spectrum of free n equals to 4 superangles. And the dictionary that you have in mind is, you see, in free n equals to 4 superangles, you take any of the fields that live in your n equals to 4 superangles, and then you look at single trace vertex operators. So you have you can put W things into the trace. Each of these W things is one out of this list. This list is basically in one-to-one correspondence with the singleton representation. So you get W copies of the singleton representation, and because it's in the trace, it must be cyclically invariant. So if you count all the states that live in the W-fold tensor product of the singleton representation that are invariant in the cyclic transformation, you reproduce exactly the free superangular spectrum, and they match exactly with the states, the physical states that survive in the W spectrum flowed sector of our proposed worldsheet theory. So this looks very much like a string bit picture where the string really looks like a spin chain with W sides. At each of these sides, you have this twistor valued string bits, and the physical state conditions just guarantee that you keep cyclically invariant piece and thereby reproduce manifestly the spectrum of free n equals to 4 superangles. So this is obviously, there are gaps along the way. We don't have a first principle derivation of why exactly this is the physical spectrum, but quite remarkably, it is my opinion, if you impose what looks like fairly natural constraints, you reproduce exactly the spectrum of free n equals to 4 supermills. So we are very optimistic that we are on the right track towards finding the worldsheet theory that's really dual to free n equals to 4 supermills. So since my time is, actually, I don't exactly know when I started, but I think my time is more or less up. So let me conclude. So I think for the case of ADS3 cross S3, we understand things in great detail. There is a free field realization on the worldsheet. We've really shown that it matches exactly all the structure that you expect from the symmetric orbifold theory. There we have a very concrete understanding of how this goes. And given how this fits together, there is a very natural generalization of this that you could believe should be the right description for ADS5 plus S5. And it consists of basically doubling the symplectic bosons and free fermions that appear in this free field realization. And then with some assumptions about the structure of the physical state condition that we haven't yet derived, that sort of somebody, maybe us, has to redo Berkowitz-Wafer-Witten in this more general context. We have managed to reproduce exactly the correct single trace spectrum of free n equals to 4 supermills from our worldsheet model. And this at least has a chance to open the door for the proving the ADS-CFT correspondence. I think this is closer than anybody has managed to get before, writing down a string theory that has even remotely a chance to describe n equals to 4 supermills. I think our theory has a very good chance to do so, and we see pieces of it working. Now, obviously, there's a very long list of things one needs to understand. So first and foremost, we have to understand this physical state condition from first principles. Then we would like to study the correlation functions of ADS5. That would allow you to go away from the free point. But given the fact that, remember, in ADS3, it all hinged on this incidence relation, and here it doesn't look that different. So you would expect that there is some covering map type structure that will constrain the correlation functions. And then once one's managed to do that, then one may hope that one can analyze the perturbation theory away from the free case and show that you don't just reproduce the spin chain of free n equals to 4 supermills, but you also reproduce correctly the interactions that you have to put in order to really describe n equals to 4. Now then, secretly in the background, there's some sort of higher spin symmetry that we haven't really utilized in any explicit way, but that should be there. We know there's a Youngian symmetry from the integrability perspective. So somehow that should also manifest itself from the worldsheet viewpoint. And I think that would be very interesting to understand, because that will probably also help you how to show that this really reproduces the spin chain answer. I mean, at the end of the day, you would expect that, say, the correlation functions and the perturbation analysis, the way it will work is that it will just manifestly reproduce the spin chain result. That's what you would expect this worldsheet theory to do. And then, because the spin chain reproduces correctly n equals to 4 supermills, you'll basically be done. If you can show that this worldsheet theory really conspires to just reproduce the spin chain. Now, then there are some other, maybe less important points. So it gives you a slightly new view on the spectrum of n equals to 4. It looks a little bit like these variables that appear in the hexagon approach to calculate the correlator. So there are some similarities to other approaches that have appeared. But I think the key will be to really try to understand exactly how these correlation functions work and see that you really reproduce the spin chain from this worldsheet description. But then you would have an honest string theory that reproduces the correct spectrum and structure of n equals to 4 supermills. And I think that would be a very good starting point to assessing all sorts of aspects of the ADS-CFT correspondence. So I'll stop here and thank you for your attention.
Very much. Questions?
Yeah, I have questions. So I remember that the hybrid formalisms contains in the chiral bosons rho. Actually, it was playing a quite important role. Does it play the same role, some role also in your analysis? I remember this chiral boson was very problematic when you try to do high loop computations because it creates some physical poles in the calculations. Does it play some roles here also in your analysis?
Well, I mean, for ADS3, it surely does. I mean, for ADS3, we are purely in the world of Berkowitz-Wafer-Witten. So we have the rho field and the sigma field, and as well as the PSU sector. And the PSU sector we've also described in terms of free fields, but these ghosts are definitely there, and they're there to describe the cohomology. In fact, that's in some sense what we are trying to do in understanding how to describe correctly the physical state condition from first principles. The question is, what sort of ghost fields will you have to introduce for ADS5 cross S5? What are the cohomology operators you have to define, and how will this generalize the ADS3 case?
I also remember that in the Berkowitz ADS5 cross S5 twistor theory also contains some other sector, not only the Z and Y field, but there are other sectors.
Absolutely, yes. So this doesn't appear for us. So what he did, he had the Z's and the Y's, and then he put in this current algebra of C equals to 26. That doesn't, and he believed that that's how the gauge symmetry would emerge. But then he didn't have any, he put in something else, and he didn't have any spectrally fluid sectors. In our theory, there is no additional sector. Everything comes from the symplectic bosons and the fermions, but they become, or from this PSU2, 2/4 sector, but they become more interesting because of the spectral flow. So they generate all the degrees of freedom coming from the spectrally fluid representations. And I mean, they're effectively topological, which is the reason why all of these out of the wedge modes disappear. I mean, in some sense, that just tells you that all of it just comes from this spectral flow. And so in our description, there's no additional degrees of freedom except for ghost fields of the kind, of the rho kind and the sigma kind. But everything else just comes from these free fields that underlie the PSU2, 2/4 theory, together with its spectrally fluid representations.
Thank you.
There was a question from the Zoom, Volker.
Thank you. Hi, Matthias. Thanks for the nice talk. So actually, we played with this similar things, mostly motivated by Nathan's work some 10 years ago, and noticed that we could embed sort of the spectrum into these wedge modes. At the time, I thought to kind of remove these other modes by interpreting the model as a fully gauged Westermino model, so that only sort of these spectrally fluid wedge modes would stay in the spectrum. Do you have any thoughts on this?
Well,
so this would be sort of a mechanism to remove all the other modes by some kind of concrete BRST operator, I would say.
Well, so I think we come from sort of what we've seen to work explicitly for ADS3 cross S3. So for ADS3 cross S3, it all came just from the physical state condition a la Berkowitz-Vafa-Witten, and you didn't have to gauge by some global symmetry. I mean,
as you pointed out, it's sort of very special because lots of many of these degrees of freedoms were removed already, right?
Well, but I mean, here it's the same thing, right? Because I mean, once you've introduced the symplectic bosons and fermions, also for PSU2, 2/4, I mean, this is again a level 1 theory. So again, many of these things are already, I mean, it's much smaller than a generic PSU2, 2/4, because you're sitting at level 1. So there it's very special. And I think that will mirror very, very naturally what happened for ADS3 cross S3. So given our experience with what happened for ADS3 cross S3, we don't see any need for this, for gauging some global group. And we expect it'll rather come from, you see, I mean, you would expect this theory to be more supersymmetric than the Berkowitz-Vafa-Witten theory. I mean, the Berkowitz-Vafa-Witten theory has an n equals to 2 algebra that commutes with the PSU 1,1/2. But here, basically, your theory is double as symmetric. So it doesn't strike us as being implausible that there will be an n equals to 4 algebra that will commute with the PSU 2,2/4. And then the n equals, if you imply the physical state condition of an n equals to 4 algebra, that just will kill all the degrees of freedom. And then you just have to be careful what are zero modes and what are non-zero modes. So that's the way we believe this will pan out. And we feel that's the natural, I mean, I think different to your situation, I think by now we really understand the ADS3 cross S3 case in great detail. We really see exactly how it works. And that suggests a quite natural generalization to ADS5 cross S5. And I don't really see why it should work any differently than in ADS3 cross S3.
Okay, yeah, as you say, I mean, we didn't have, of course, all this work of yours on ADS3, so we were mostly motivated by Nathan's work. I see, this is interesting. So can you say a few words on correlation function? Because I remember that we also played trying to reconstruct big constructions, so I would be very interested.
But I mean, this is, I mean, this is this slide, which is, I mean, it doesn't do this total justice, but this is a very remarkable fact about this correlation function. It hinges exactly on defining the vertex operators correctly. So so the key point here is that the vertex operators depend on X and on Z. So how do they depend on Z and on X? Actually, maybe I should add a slide so I can explain this a little bit. So you know, I mean, a vertex operator as a function of Z, you know how you describe the dependence on Z. You simply describe it by conjugation by the translation operator. L-1 is the translation operator on the worldsheet. Now, if you want to, these vertex operators also depend on a space-time coordinate, which you should if you want to calculate space-time correlators, then you should modify this by also translating it in space-time. But you know what the translation operator is in space-time, and in terms of this language, it's just xj plus, and then it's e to the minus xj, and then it's 0, 0. So this is basically canonical because, I mean, you have a vertex operator at some position and you translate it by the translation operator in space-time and on the worldsheet, and these two things commute with one another, so there's no ambiguity in how you define it. But this has enormous consequences for how the spectrally flowed representations behave. Because you see, when you bring, say, J minus close to this field, because J minus doesn't commute with e to the xj plus, you generate a term that will go like x squared times the p's that go like j plus. And if j plus has a pole and j minus has a 0, then j minus will acquire a pole, but it'll go proportional to x squared. So once you take this in, you can actually derive ward identities that characterize the correlators of the spectrally flowed the vertex operators. And that's what we did in this paper together with Lawrence. So we studied the SL2R ward identities. And then from these ward identities, you can show, well, actually, we could only show it ultimately in the free field case, but you can show that you get very stringent constraints on the spectrally flowed vertex operators, and the X and the Z variables get intimately linked together. And as a consequence, what turns out is that these correlators are actually proportional to delta functions in that. So for example, when you look at a 4-point function with all W's being equal, then you can obviously choose the 3 X's and 3 Z's to map into one another under the Möbius transformation. And then the correlator will only be non-zero if the 4th Z gets mapped to the 4th X. So it will be, strictly speaking, proportional to a delta function. And then if you integrate them over the worldsheet, you'll really just pick out the one point in moduli space where the holomorphic covering map exists, and you reproduce exactly the map of the covering. So this is really an honest derivation of these spectrally flowed vertex operators, but it comes from being very clear about how to define these vertex operators. Now, in the case of ADS5 plus S5, you would think that something very similar will happen because you see the ingredients are exactly all the same. I mean, you have the same symplectic bosons. So in terms of these free fields, you get this sort of relation. Now we're going to get a number of relations of that kind. And what we are currently struggling a little bit with is to understand exactly what's the correct function, what are the correct covering maps. I mean, there must be covering maps. There must be maps from CP1 into CP3 with certain properties, and we are trying to count them and understand how localized they are. But we believe there's an interesting story here, and we are pretty confident there will be some delta function localization. And our suspicion is that that will just reduce this correlator basically to a spin chain calculation. That's sort of what ultimately will happen. Because I mean, this worldsheet theory just wants to be a spin chain description. It's sort of the stringy version of it. And this delta function type behavior is the sort of thing that will localize it to something that looks like a discrete spin chain. So that's something we are currently working on, but we haven't quite, we're still struggling a little bit with the algebraic geometry and the exactly of what characterizes these holomorphic maps and so on. So we are not quite there yet. So this is what I'm referring to here.
Thanks a lot. Yeah.
Okay, thank you. Other questions? Can you say something about the perturbations in the ADS3 case?
That's a very good question. So that's also something we are trying to do at the moment. So in the ADS3 case, you know what you have to do, right? In the ADS3 case, there's one interesting vertex operator that deforms the symmetric orbifold away from the symmetric orbifold point. That's the two-cycle twisted sector exactly marginal operator. Now, because we have this dictionary, we know exactly which vertex operator on the worldsheet it corresponds to. So therefore, the perturbation theory of your symmetric orbifold should be reproduced by perturbing your worldsheet theory by that very specific physical vertex operator. And because we have these correlation functions under control, they are just labeled by this delta function localized covering maps, we should be able to work this out and reproduce the correct structure of the perturbation theory that people have calculated for the symmetric orbifold. Now, it's technically a little bit difficult because the perturbing field is not a ground state, it's a symplectic boson descendant. So you have to wrap the symplectic boson mode in some complicated fashion and so on. So we are still struggling a little bit with the technicalities, but I think all the ingredients are there, and it's just a matter of sitting down and doing it to show that this reproduces correctly the perturbation theory of the symmetric orbifold away from the symmetric orbifold point. And this is sort of the toy model calculation that we hope will then also generalize in a very similar manner to ADS5, but obviously there we are further away yet.
Okay. If there are no other urgent questions, let us thank Matthias one more time for his talk.